This is lesson 5.3 on circumcenter and incenter of triangles. So first of all, term, concurrent lines. 3 or more lines, and this should say, and they could be rays or segments, this should say in a plane. 3 or more lines or rays or segments in a plane that intersect in a single point are called concurrent. So that point of intersection is called a point of concurrency. And I'll draw you a picture of this in a minute here. So concurrent lines look like this. If you have at least 3 lines that are all intersecting in a single point. So that point right there is called the point of concurrency. And you have to have at least 3 lines that intersect. Now, the way you don't want it to happen is like this. Those lines are intersecting pairwise. 2 lines are intersecting each other, but they're not all 3 intersecting in a single point. So these would be not concurrent. Whereas the purple lines are concurrent. So this whole chapter is about different kinds of segments that are in a triangle. In lesson 1 we talked about mid-segments. Lesson 2 we're talking about perpendicular and angle bisectors. And then 3 we're talking about perpendicular and angle bisectors and how they act in a triangle. So first of all, in a perpendicular bisectors in a triangle, since there are 3 sides in a triangle, there would be 3 perpendicular bisectors. So what you're seeing in this picture down here is we started with triangle ABC. So this large triangle here that you see, ABC, that's what we would have started with. Then, perpendicular bisector, perpendicular bisector, and then perpendicular bisectors were drawn of all the sides. Now, notice that all the perpendicular bisectors are concurrent at a single point. That point right there is P in this picture. Okay, the perpendicular bisectors are the red segments, and they're concurrent at a point which is labeled P in the diagram. So the conclusion here is that the distance from P to A, and it's a little bit thick, from P to A, P to B, and P to C are all the same. Now, why is that happening? Well, remember the perpendicular bisector theorem. If you look at one of these triangles, so let's say you look at this triangle right here. Okay, so if we look at, say, this triangle here. If we draw in the perpendicular bisector of that segment, then any point that lies on that perpendicular bisector, in particular, point P here, then that point, because it lies in the perpendicular bisector of the triangle, the distance to each endpoint of the segment are the same. So P is equidistant from A and from B. And then if you do the same thing on another one of those triangles, so if we looked instead at this triangle over here, okay, draw the perpendicular bisector, choose point P on the perpendicular bisector. Because it lies on the perpendicular bisector of the segment, it'll be the same distance from each endpoint. So that's using the perpendicular bisector theorem multiple times. And we can conclude that these segments are all congruent to each other. Now, We're going to talk about that in kind of another way of thinking about that, why that makes sense. But that point P is equidistant from the vertices, and that's using the perpendicular bisector theorem. So the point of concurrency of the perpendicular bisectors is equidistant from the vertices of the triangle, and it has a special name which is called the circumcenter. Now, the reason it's called the circumcenter is because, as you see in this picture down here, a circle can be circumscribed around the triangle. So starting with any triangle, if you draw in the perpendicular bisectors, they will all be concurrent at a single point. And that point right there is called the circumcenter. So in this diagram, we have started with, it says highlight the perpendicular bisectors there. The perpendicular bisectors are segments here that are cutting those segments at their midpoint and forming a right angle. So perpendicular bisector, and then perpendicular bisector. So the point where they all come together is called the point of concurrency, which is called the circumcenter when you start with perpendicular bisectors. And again, the circumcenter is equidistant from the vertices of the original triangle. So P to A, P to B, and P to C would all be the same. PA, PB, PC are all the same. Now, an easy way to remember that is that because it's called a circumcenter, that means you can circumscribe the circle around the triangle, and circumscribing means that each one of the vertices lies on the circle and you can tell that each of those lengths is a radius of the circle. Okay, so over here, the circle is circumscribed about the triangle, with P being the center. And again, P is called the circumcenter of the triangle. It would be the center of the circumscribed circle. So you would place your compass on the circumcenter, the little tip on the compass on the circumcenter, stretch it out a length of a radius, and then swing it around to draw the circle circumscribed around the triangle. And then each of those distances is a radius, so that makes sense why those distances are all the same. So the circumcenter is equidistant from the vertices of the triangle. Now, for triangles, every triangle you can draw in the three perpendicular bisectors, but the kind of triangle will determine where that circumcenter, that point of concurrency, will lie. So the circumcenter of a triangle can be inside, on, or outside of the triangle, depending on what kind of triangle it is. So here's an acute triangle. If you had drawn the perpendicular bisectors, now they've shown the right angle there. They did not put the marks on that, so you should indicate that those are perpendicular bisectors by putting the marks. I didn't notice that when I copied the picture. So we want to make sure we can tell it's hitting at a midpoint, so they're perpendicular bisectors. The point of concurrency is where all of them come together. Now, notice that if the triangle is acute, then that circumcenter will be inside of the triangle. And if the triangle is a right triangle, then the circumcenter is on the triangle. So here's the perpendicular bisector, making a right angle, so these are congruent. And this perpendicular bisector, those are congruent. And this perpendicular bisector, these are congruent. So again, our point of concurrency is right there. Now, if it's a right triangle, the circumcenter actually lies on the triangle, and it will be at the midpoint of the hypotenuse. It's at the midpoint of the hypotenuse. You can tell that's the midpoint because since this was a perpendicular bisector, that divides those segments into congruent parts. So this is the midpoint of the hypotenuse of the triangle. Now remember that this would be the center of a circumscribed circle. So we can draw a circle around the acute triangle, or around the right triangle, or around an obtuse triangle. So for the obtuse triangle, here's your perpendicular bisectors. So again, mark those parts congruent. These two parts will be the same. And then for this one, you'd have 3 marks here and 3 marks here. Okay, and then again, the point of concurrency would be that point right there. That's the circumcenter, and the circumcenter will be outside the triangle. Now, you should notice that for this obtuse triangle, where the circumcenter is located is sort of across from the obtuse angle. So it's outside of the triangle, but more specifically, it's always going to lie kind of outside of the longest side of the triangle. And the more obtuse the angle is, the further away that point will be. So the closer it gets to being a right triangle, the closer it moves in, and it would end up, like in this picture, it would end up here if it were actually a right triangle. So now we're going to talk about how you could apply this in a problem. Okay, so for the first example, we're going to talk about a picture where you've got 3 boats, and we're trying to locate where there would be a buoy. The buoy is supposed to be the same distance from each one of the boats. Remember that a circumcenter is equidistant from 3 vertices of a triangle. So if we go ahead and draw in a triangle here, then if we make the perpendicular bisectors, where they intersect, where they are concurrent at the circumcenter, would be where the buoy would be located. So we're just sketching this, eyeballing this. You can tell that this is a slightly obtuse triangle. So based on what we just talked about, you should know that the circumcenter should lie a little bit outside of the triangle. So if I draw a perpendicular bisector there, and a perpendicular bisector here. I really don't have to draw the third one, because since they're concurrent, I know that the third one would go through that same point. But here's your last perpendicular. That's not a very good one. Here's your last perpendicular bisector, so it would cut there, and the circumcenter would lie there, and that's where the buoy should be located. All right, so you would construct the perpendicular bisectors, or draw, in this case, sketch. Make the perpendicular bisectors. The circumcenter is where the buoy should be located, because the circumcenter is equidistant from the triangle's vertices. Okay, next example. The perpendicular bisectors of the triangle PQR meet at point S. So these are the perpendicular bisectors. And again, they have the markings here. And it's asking you how long PS and QS are. Well, those represent the distance from S to Q and S to P and S to R is all the same, because that point is the circumcenters, the point of concurrency, the perpendicular bisectors. So since SR is 10, S is a circumcenter. Oops, misspell. Circumcenter. S is a circumcenter, so S to P and S to Q and S to R are all equal, which means that PS and QS are each 10. Alright, now we're going to talk about angle bisectors in a triangle. So because a triangle has 3 vertices and therefore 3 angles, that means that it's going to have 3 angle bisectors. So there's a theorem about the angle bisectors. If you start with triangle ABC, so here's triangle ABC, there would have been a blank triangle sitting there. If you could draw in the angle bisectors, so there's an angle bisector, there's an angle bisector, and there's an angle bisector. You can tell that these are bisectors by the markings here. 2 congruent angles there, 2 congruent angles there, 2 congruent angles there. It's kind of hard to tell that there's 2 arcs on each of those angles and 3 on each of those. They're really, it's like this on one side and then 3 more on the other side. They're not 3 big arcs. There's 3 little arcs on either side of the picture. Okay, so those were angle bisectors. The angle bisectors are also concurrent in a single point. So point P is the point of concurrency for the angle bisectors. The angle bisectors' point of concurrency is called the incenter. Okay, circumcenter is a particular name if you started with the perpendicular bisectors. We're starting with the angle bisectors this time. Now, using the angle bisector theorem, if you pick a point that is on an angle bisector, then it is equidistant from the sides of the angle. So if you look at just this angle right here, this is an angle bisector. Any point on the angle bisector is the same distance from each side of the angle. Okay, which means that in this picture, those 2 segments are congruent. Now notice that they're doing the perpendicular distance because that's how you measure distance from a point to a line. The distance from point P to each side of the angle, it has to be the perpendicular distance. Now if you were to do the same thing for angle C, for example, every point on angle C is the same distance from the 2 sides of angle C. So in particular, PZ and PY will be the same. Again, you have to be measuring the perpendicular distance. Okay, so in this picture, PX, PY, and PZ are all the same length. And again, we're starting with the angle bisectors. The bisectors of the angles. Now, that means that that point is the same distance from the sides of the triangle, not from the vertices this time, but from the sides of the triangle. Now, the reason that it has a special name incenter is because it can be inscribed in the triangle, it looking like that down there. So the center of the circle would be the incenter. This point right here is the incenter. And then the circle's inside the triangle this time. So in this triangle ABC, you would have started by drawing in the angle bisectors, which again you can tell they're bisecting the angles because of the markings that you're seeing in the corners here. The angle bisectors are concurrent at a point which is called the incenter of the triangle. Okay, we highlighted the angle bisectors, and I'm doing it with purple here. The circle that can be inscribed inside of the triangle, it's inscribed this time. We'll use P as the center of the circle. And this time, because the incenter is equidistant from the sides of the triangle, each of those segments represent the radius. So again, the distance from a point to a line is the perpendicular distance. That's why those right angle marks are there. And we would have PD, PE, and PF all being congruent. Each of those lengths is a radius of that inscribed circle. Now again, it's inscribed because it's inside the triangle. Each side of the triangle is a point on the circle. So instead of the circle going around the triangle, where that's called circumscribed from the perpendicular bisectors, we have an inscribed circle that's coming from the angle bisectors. Now, on the perpendicular bisectors, the circumcenter, remember we said that the point could be inside on or outside of the triangle? Why does it make sense that it would always be inside? Why would the incenter always be inside the triangle? Well, the center, the incenter is the center of the circle, and if it gives you an inscribed circle, of course the center of the circle is inside if the entire circle has to be inside. Okay, so the incenter is the center of the inscribed circle, so the center of the circle has to be inside of the circle, therefore it's inside of the triangle. Okay, and then one last example here. The angle bisectors meet at point W. So they're telling you that if you were to bisect, they didn't mark it on here, but they're telling you that these are angle bisectors. If you were to draw in the angle bisectors, you would locate the point of concurrency at W, and that would be the incenter. Okay, so W is the incenter in this picture. Because it's the incenter, the distance to each side from the incenter is the same. So they want you to find the value of D. Well, since we know that XW and WZ are congruent, so that means that 2D plus 7 would have to equal 4D minus 1, which gives you 2D equals 8, and D equals 4. It just asked you for the value of D, so then you're finished. This is the end of lesson 5.3.